Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the next training in the summer weather training series. And today I'm going to cover the topic of fronts, the different type of weather fronts out there. And there's many different ones. As you can tell by the title slide here, there's different symbols that represent different types of fronts, whether we're talking about a cold front, a warm front, a stationary front, as well as an occluded front. So let's get right into the details on these very important weather features. Starting off with the definition of a front, a weather front, it's a zone of transition between two air masses of different density and temperature. And when I talk about different density, I definitely need to mention different moisture levels, whether it's dry or moist. That's a big part of the density of the air, along with that temperature. Now, fronts are associated with major weather changes. The frontal types overview: cold front is one that moves in a direction in which cold air is going to displace the warm air at the surface. And with the cold front, cooler, denser air slides beneath warmer, less dense air it is displacing. Another general overview of a front is a warm front. A warm front is one along which warmer air replaces colder air. A warmer air mass is basically moving in toward a cooler air mass. As that cooler air retreats, that warmer air mass moves in. So that's a warm front. Another type of front is known as a quasi-stationary front, and this is one along which one air mass does not appreciably replace the other. So we have fronts that are termed stationary fronts, and they generally move at a speed under 5 knots. Don't really move a whole lot. And then lastly, we have, on the overview of fronts, occluded fronts. Now, occluded fronts, these are ones where a cold front overtakes a warm front, and it forces the warmer air up off the ground, and it may be either a cold or a warm type of occlusion. And we'll get more into detail on all of these fronts as we move along in today's training. Now, where are the most favorable locations for fronts to form? For the northern hemisphere, the primary frontal zones are going to be the Arctic frontal zone and the polar frontal zone. Now, most important frontal zone affecting the United States is the polar front. And there's a big background, if you want to Google this. It's really cool stuff. The polar front theory, at which a front generally lies in the position around 60 degrees north latitude in the northern hemisphere, and multiple areas of low pressure will develop and move along these fronts, and they tend to be very stormy zones at those latitudes, at 60 degrees north and south, where you have the clash of the milder mid-latitude westerlies meeting the much colder polar easterlies. Now, the polar front, this is a region of transition, as I mentioned, between the colder polar air and also the warmer, milder air of the mid-latitudes. And that polar front can sink, and it does sink frequently during the winter season, down into the lower 48 in the United States, and where you'll get much colder continental polar air moving southward, clashing with maritime tropical air moving northward from the Gulf of Mexico. It's very frequent to have the polar front much further south, along with that polar front jet stream in the wintertime. So during the winter months, that polar front is going to push farther southward, but during the summer months, the polar front will seldom move farther south than the central United States. Here's a great map to just kind of get you familiar with favorable frontal locations. And I went ahead last week's video and covered air masses, and I wanted to introduce you to those air masses because a frontal location is basically the point at which these air masses collide. And if you want a great refresher on air masses, please watch last week's training video on air masses and the very different characteristics associated with each of them. But in general, you'll notice on this graphic how you have a polar front across the Pacific Ocean, you have a polar front across the Atlantic Ocean, and this is in January, by the way. Now, the positioning does change throughout the course of the year between January and, let's say, July. In January, the polar front is much further southward in association with much more favorable upper level dynamics with the polar front jet stream overhead and how that dips down into these big troughs and these amplified ridges. But in general, you can see in the wintertime, the polar front extends from about 30 degrees north latitude to about 45 degrees north latitude, right in that range. You'll also notice in the southern hemisphere that you have polar fronts generally positioned to the west of the tip of South America there, as well as a very favorable location where you get a lot of explosive storm development is off the coast of Australia, in the vicinity of the Roaring Forties south of Australia as well. You get some really intense cyclones that develop along the polar front in the southern hemisphere. Right, so now that we're somewhat familiar with the different types of fronts, and in general, where the favorable areas for where these fronts to form, we're now going to talk about frontal slopes. And this is very important when we talk about slopes. Now, a cold air mass, it's heavy, it's dense. It tends to hug the ground and stay close to the ground. It acts like a wedge and tends to undercut a lighter, more buoyant, warmer air mass. Now, the cold air is going to be below because it's heavier and denser close to the ground, and warm air is above the surface of these frontal slopes, above surface fronts. Now, the wedge of cold air is going to produce a slope on the order of 1 to 50. So that first number, the 1, represents 1 mile in the vertical. So if I were to be standing on the ground, I look straight up overhead, up to the sky, that's 1 mile high, okay, in the vertical. The 50 refers to 50 miles in the horizontal. So now I'm looking straight at the horizon, straight ahead, and that's going to be the horizontal view. So the slope of a cold front is fairly steep at 1 to 50, whereas the slope of a warm front is much broader, a more gentle slope ranging between 1 to 300, 1 mile in the vertical, and 300 miles now horizontal. So we're talking about a location, for example, from Virginia Beach, perhaps over to the western part of Virginia, like Staunton area. That would be the slope of a warm front. So it's much more broad, yeah. Here's a look at a graphic just showing you what the frontal slopes look like. So on the left, I have this cold frontal slope. So you see the arrow there, but the cold air moving in. And you can see how more steeply sloped that cold front slope is. And then look at the graphic on the right here, the right-hand portion of this graphic, showing the much more broad or gentle slope of the warm front. As warm air is lighter, it's going to ride up and over the retreating cold air. Now, this is very important to the type of weather you get. In addition, when you have these frontal boundaries, a front is simply an area where the winds are coming together or converging. And when the winds converge or come together in the low levels along the ground, they meet, and then the air rises in the vertical. And so a front is an area where you typically find clouds, and you typically find some sort of precipitation, since it's an area of convergence. So we already have, with this low-level converging air along fronts, it's already a favorable situation to get rising air, and then you get these wave cyclones that develop along the fronts. And these wave cyclones are usually associated primarily with cold fronts, but they also can develop along stationary fronts as well. Now, cyclogenesis is simply a fancy way to say the development of a storm. These tend to occur on what's known as this frontal trough. And a trough is simply just an area of lower pressure or height in the atmosphere. Now, the cyclone is going to develop along this frontal surface, and it's developing gradually upward as the cyclone deepens. So it grows with height as this wave cyclone or storm system develops along the front. The circulation tends to increase in the vertical with height over time as that cyclone gets much stronger. The middle latitudes between 30 and 60 degrees latitude are the regions where the cold and the warm air masses continually interact and meet. This interaction coincides with the location of the polar front. So what I'm looking for when I want a favorable area for a front to form is a sharper temperature contrast across the front. And we have a lot of the favorable geography in the United States, east of the Rocky Mountains especially, where we get this very cold, dry air. It's heavy, it's dense, coming down from Canada, and then warm, moist air coming up from the Gulf of Mexico, which is much lighter. So you get this major clash of air masses along these fronts. Now, when the polar front moves southward, for example, in the wintertime, it is usually associated with the development and movement of cyclones and subsequent outbreaks of colder air as those cyclones move along to the east. You get much colder air in the backside of these cyclones. The cyclonic circulation associated with the polar front tends to bring polar air southward on the backside of these cyclones and warmer, moist tropical air northward on the front side of the cyclones. This is a process of heat transfer because the equatorial areas near the equator is much warmer on the Earth compared to the much colder polar areas. So this is the way the atmosphere redistributes that temperature imbalance, bringing warm air northward and cold air southward. During the winter months, the warm air flow usually occurs over the water, and the colder air usually moves southward over the land areas, and then the situation is reversed in the summertime. Now, these large cyclones or storm systems that form on the polar front are usually followed by smaller additional cyclones, and these are referred to as cyclone families. Every moving cyclone is going to have two significant lines of converging air distinguished by these thermal or temperature properties. The discontinuity line on the forward side of the cyclone or that storm, the low pressure area, where warm air replaces cold air, that's going to be known as the warm front. And typically the warm front is going to extend east to northeastward from that center of low pressure, the cyclone itself. The discontinuity line on the rear portion of the cyclone, where cold air comes in and displaces warm air, that's known as the cold front. So when the wind, the temperature, the pressure, and these upper level influences are just right, you get these waves of low pressure or cyclones that form along the polar front. Now there are two wave types when we talk about in the weather business. There's two main wave types we're interested in looking at. One is known as a stable wave, and the other is known as an unstable wave. Stable waves are the ones that neither develop nor occlude, but appear to remain in the same state. So I want you to think of stable waves as not really intensifying. They basically just move along the polar front. They don't really reach the occlusion stage, which is a very intense stage for a cyclone. Again, just remaining the same strength throughout their life. Stable waves usually have a smaller amplitude. They usually have weaker low pressure centers and have a fairly regular rate and direction of movement. And again, they do not grow into the occlusion stage, which is much more intense. So now if I'm looking at the graphic here at the bottom of this slide, initially we have the polar front. It's just sitting there, it's stationary. It's not really moving much. You have cold air to the north of the polar front, and it's generally, you see the arrow pointed towards a westerly direction, from east to west. And then below the polar front, you have this warmer air mass. And see how they're parallel to each other, the arrows? These air masses are on each side of the front, the cold and warm, but they're not really turning into each other until part B, where we get the formation of a wave, a stable wave to form along the polar front. And now you're starting to see the arrows kind of turn inward towards each other at that point B. And then finally at point C, you actually get that wave to develop a little further, and you get the development of a warm front. Warmer, moisture air is represented by the lighter arrows there on the bottom right, and the colder air is on the back side of that cyclone, represented by those darker arrows. Now, we talked about stable waves, but there's also something known as unstable waves. Now, these are the most common type of wave that occur along the polar front. The amplitude of this wave is going to increase over time, which is going to occur basically up until the occlusion process. The formation of a deep, intense cyclone or storm system along with the occluded front is going to initially break up the polar front. And when the occlusion process is complete, the polar front will reestablish itself for the next wave cyclone to develop along it. So initially, in the unstable wave, initial stage of development, the polar front is going to separate the polar easterlies from the mid-latitude westerlies. And then you're going to have this uneven local heating. You'll have sometimes irregular terrain or mountainous areas mixed in, or this wind shear, which is a change in wind direction or speed with height. That's going to be major between these opposing air streams of warm and cold air masses. This may eventually start a wave-like disturbance or a perturbation on the front. And if this tendency persists and the wave increases in amplitude, we get a counterclockwise or a cyclonic circulation around that cyclone in the northern hemisphere. This is going to set up with one section of the front moving northeastward as a warm front, while the adjacent section of the front moves southeastward as a cold front. Now, pressure at the peak of the frontal wave is going to fall, and you're going to get this low pressure center or area to form. The cyclonic circulation then becomes stronger and stronger over time, with these wind components becoming more perpendicular to each other. And that perpendicular wind component is going to push the fronts. Again, the warm front typically moves, the warm front's going to move from the southwest toward the northeast in the northern hemisphere, while the cold front is going to move from the northwest to the southeast. Westerly winds are going to turn to southwest winds ahead of the cold front. It's going to push the eastern part of the front northward as that warm front. And meanwhile, you have the easterly winds on the western side of the cyclone, which are going to turn to northerly winds and then push the western part southward as a cold front. Now, the cold front, because of the density of the air mass behind the cold front, it's much colder. A lot of times it's drier, so it's much heavier. It's going to move faster. It's going to be able to pick up a lot more momentum as it moves forward. And that eventually is going to result in the occlusion, where the cold front eventually moves faster than the warm front. The cold front will then overtake the warm front because it's moving quicker, and then closes off the warm sector of the cyclone, and you get the occlusion to form. And this is the time where the cyclone or storm reaches its maximum intensity during the occlusion stage. And as the occlusion continues to extend outward, the energy gets dispersed over a greater area, the cyclonic circulation eventually weakens, and the frontal movement slows, and you get much more mixing of the air masses. Eventually the air mass contrast diminishes, and you get the decaying of the wave cyclone. Now, sometimes you get a new frontal wave that'll form at what's known as the triple point. The triple point is the area associated with a cyclone where all the fronts are intersecting with each other. So you have an occluded front, cold front, and warm front. There's a point right there where all three of those type of fronts meet, and that's known as the triple point. And if you got the right upper level jet stream dynamics, you can actually get a new wave cyclone to develop on the front. So in the final stage, the two fronts are going to become a single stationary front, again reestablishing the polar front. So here's the unstable wave stages and characteristics. If you look at the graphic on the left, you again see in point A how the cold air and the warm air, polar easterlies, the mid-latitude westerlies, they're separated across the stationary boundary at A, but they're not really turning in towards each other. They're moving parallel to each other until point B, where we get that unstable wave start developing along the frontal boundary. And now we're starting to get a little bit more momentum. The cyclonic circulation is increasing at point B, and now we have a warm front moving toward the northeast, a cold front moving to the southeast. C, you definitely can see that at point C, where you get the frontal wave fully developed at this point. The surface pressure is falling at this point as well. Your winds are picking up in speed. You got southwesterly winds ahead of the cold front. You have more of an easterly, east-southeast wind ahead of the warm front, and then you got these northerly and northwest winds behind the cyclone, behind that cold front. At point D, the unstable wave cyclone is getting stronger, more intense. You're getting greater momentum. The colder air is heavier and denser. It's moving much more quicker than that warmer, milder air out ahead of the cold front. And then by point E, now you're reaching the occlusion stage, where a portion of the cold front has now caught up to the warm front and lifted the warm air completely off the ground, pinching or closing off the warm air sector of the cyclone. And at point F, now you have a much weaker cyclonic circulation, and you'll notice the descriptors of the air masses the air mass contrast is pretty much diminished by point F after the peak intensity of that storm or wave cyclone is established. Point G, now you have a reestablishment of the polar front, where you're getting the colder air to the north and the warmer air to the south. And again, if you have the right dynamics in the upper levels, especially at the jet stream level, then you can get the development of a new wave cyclone. If you look at the overall characteristics on the right-hand portion of the slide, you'll notice that initially at the wave cyclone development at the 0 hour, your central pressure may range from 1,000 to 1,012 millibars. But by the time we reach occlusion, 12 to 24 hours later, that cyclone is much more intense at the occlusion stage. The barometric pressure is quite low at the beginning of the occlusion stage, 988 to 1,000 millibars. And then deepening or getting even stronger with much lowering pressure by the mature occlusion stage, where that cyclone is reaching its peak intensity between 984 and 968 millibars. And then finally, cyclolysis, or the decaying of the wave cyclone, there where the pressure begins to rise once again. And you'll notice the direction of movement as well is indicated, as well as the speed of movement. How these wave cyclones start off moving fairly quickly, but then as we get the cyclonic circulation increasing, you notice how they slow down. So initially with the wave cyclone, the speed of movement of the cyclone may be 30 to 35 knots. By the time we reach max intensity or peak intensity at the mature occlusion stage, now we're at only 10 to 15 knots forward motion. So it slows down as it deepens or gets stronger generally. And it eventually changes direction, initially going from northeast to southeast quadrants, eventually moving towards the north-northwest in the mature occlusion stage. Right, so now frontal characteristics, let's move on to this topic. Overall, it doesn't matter what type of front we're talking about, we usually have warmer air located above colder air. If you look at the bottom right-hand graphic, you'll notice this is an example of a vertical sounding in the atmosphere, which shows the solid dark line in the bottom right graphic there indicates temperature, and the dashed dark line indicates the dew point, the level of moisture in the atmosphere as we go up in the vertical, higher up off the ground. And you'll notice that you typically get this warming with height. You see where it says accumulation of moisture here, with the arrow pointing to that part of the temperature line which kind of bends to the right. That is known as a temperature inversion. And that indicates a warmer layer of air above a colder layer of air. So temperatures are actually warming with height when this happens. And that happens a lot because warm air is always going to be either with a cold front lifted off the ground. With a warm front, warm air is going to overrun colder, denser air at the surface. If you have an occluded front, colder air is going to lift warmer air aloft off the ground. So you always have a warmer air or temperature inversion when you're talking about fronts. So a temperature inversion aloft is also what's known as that frontal inversion, where the temperatures increase with height. And its position indicates a relatively narrow layer where the normal drop in temperature with height is actually reversed. Usually with height, the temperatures will drop or fall. Strong fronts tend to have a much more distinct temperature inversion, while moderate fronts have isothermal frontal zone, which means that the temperatures pretty much stay the same with height, isothermal, and weak fronts have an actual decrease or drop in temperature through the frontal zone. So the strength of the front can definitely be determined by the strength of the inversion. The stronger the inversion aloft, the stronger the front. Additionally, some frontal characteristics that we need to be aware of. First of all, a front is a wind shift line, and that wind is going to shift in a cyclonic direction. So if you stand with your back against the wind in advance of a front, the wind will actually shift clockwise as the front passes. So that means when I say clockwise, think of the hands of the clock and how the hands of the clock generally move, right, in that general circular pattern. So in a backing wind is a change in wind direction, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And backing winds occur aloft with a cold front. So higher up above the ground, you get a backing wind, and that usually indicates colder air is moving in. A veering wind, on the other hand, is where you get a change in wind direction, which is clockwise in the northern hemisphere, and counterclockwise in the southern hemisphere, and a varying wind profile typically occurs aloft above the ground with a warm front. So the speed of the wind is going to depend on the pressure gradient. The tighter the packing of the isobars or lines of equal pressure, the stronger the wind speed as well. So that's something else to look at when we talk about fronts. And the strength of that wind is going to be highly dependent on the temperature contrast across the fronts and that pressure field. Again, the packing of those isobars or lines of equal barometric pressure in vicinity of the front. Now, one of the most important characteristics of all fronts is that on both sides of the front, the pressure is going to be higher than along the front itself. Fronts generally sit in what's known as pressure troughs, which are areas of lowest barometric pressure and lowest heights. Friction is going to do its work, though, as well. It's going to cause the air or wind near the ground to drift across isobars toward lower pressure. This causes a drift of air toward the front from both sides. So when we talk about the wind blowing across the land, right, there's a certain portion of that wind that's going to be slowed by the force of friction, because as the wind blows over fields, over grassy areas, even over rougher terrain such as mountains or through cities, the lower portion of that wind speed is going to be slowed due to friction. Friction acts opposite to the motion. So just keep that in mind. There's always a net movement of air that's going to be rising or upward, acting upward in the region of a front, because it's an area of converging air, and this is going to you're typically going to find clouds and precipitation along fronts. So weather along the fronts, now this is going to vary. This is going to vary depending on a few factors here. Cold frontal weather, first of all, is going to be different from what you'd find with a warm front. And not every cold front is going to have the same weather associated with it, by the way. The weather and intensity of the weather are largely dependent on the slope of the front. And that's why we kind of introduced you to slope a little bit. Because the steeper the slope of the front, the more vigorous the air is being lifted ahead of the front. The more shallow the slope of the front, generally you have less violent weather. Frontal slope is going to refer again to that steepness of the frontal surface using vertical and horizontal dimensions. And as a review, we talked about the average slope of a cold front being on the order of 1 to 50, 1 mile on the vertical to 50 miles on the horizontal. That's considered steep, whereas a warm front average slope of 1 to 300 is considered gradual or much more gentle. So factors affecting how steep or shallow those frontal slopes are is very important. And this includes the latitude of the front, how far north or south of the equator the front actually is located, the wind speeds associated with the cyclone that's along the fronts, and then the temperature differences or the contrast of the air masses from one side of the front to the next. And those cloud decks, the types of clouds you see that are usually in the warm air mass, they're usually going to be out there in that warm air mass because of the upward vertical movement of the warm air. Clouds forming in the colder air mass, let's say behind a cold front, are caused more by evaporation of moisture from precipitation, as that precipitation falls from the overlying warm air mass and or by vertical lifting, if you lift the air. Convergence, where the air comes together at the front itself, is going to result in lifting of both cold and warm air. Why? Warm air is less dense than cold air. So cold air is always going to be much heavier. It's going to be right along the Earth's surface, right along the ground, lifting that warm air. Stability of air masses is also going to determine the cloud and weather at the fronts, as well as the weather in advance out ahead of those fronts. Right? So we have to look at the stability of the air masses as well. We have to look at the slope of the fronts. How steep or gradual are those slopes? What about the speed of movement? How fast are these fronts moving? Are they fast-moving fronts or slow-moving fronts? So these are all factors that we think about when we want to really get a good understanding of what type of weather we'd see along these fronts, what type of clouds we would see. All right, so I want to mention briefly about these frontal intensity factors. They're very important. Now, how do we determine the difference between a weak front versus a strong front, for example? Temperature gradient, or how that temperature changes in a horizontal distance, is very useful in defining the frontal intensity. Temperature gradient, again, that's simply defined as a difference between the warm air immediately adjacent to the front and the surface temperature 100 miles from the front on the cold air side. So we're comparing, when we talk about temperature gradient, we're comparing the difference in temperature out in the warm air sector, the warm air mass, as compared to the cold air mass behind the cold front. So a weak front is going to be considered one at which the temperature gradient, that change in temperature, is less than 10 degrees Fahrenheit for every 100 miles. That's a weak front. A moderate front is classified when we have that temperature change or that gradient on the order of 10 to 20 degrees Fahrenheit per 100 miles. And then we get the strong front. Strong front is categorized or classified based on the temperature gradient, that change of temperature being over 20 degrees Fahrenheit per 100 miles. So these are the criteria that are used in determining whether we have a weak front, a strong front. You may have heard your local TV meteorologist say, hey, we have a weak front moving in or a strong front. And this is generally the criteria that's used. It's that temperature difference or gradient over 100 miles. How much of that change is occurring? Now, the frontal factors the actual weather you see along fronts. Speed of movement of these fronts is very important. Rapidly moving fronts usually cause much more in the way of severe weather, sometimes to the point where you get tornadoes, as compared to slower moving fronts. Fast-moving cold fronts often cause these severe prefrontal, basically out ahead of the front. They're known as squall lines, which are extremely hazardous, damaging winds, hail, very heavy rain. Flooding rains are possible with these. Very turbulent conditions for aviators, any pilots flying in the vicinity of these. You want to try to avoid squall lines. Slow-moving fronts, on the other hand, they're more known to produce extended periods of unfavorable weather. All right, so now let's break down a little bit more in detail the differences between cold fronts, warm fronts, stationary fronts, and the occluded fronts. We're going to really break down the characteristics of each front now. So a cold front, again, just as a review, this is the leading edge of a wedge of colder air that's moving in, undercutting this warmer air. Cold fronts are usually going to move faster and have a steeper slope than any other types of fronts. And they move very rapidly, especially if these cold fronts have these steep slopes. Remember, on the order of 1 to 50 miles, 1 mile in the vertical to 50 miles in the horizontal is an example of that steep slope. They usually have very narrow bands of clouds that occur along or just ahead of the front itself. Whereas slower moving cold fronts have less steep slopes. They're more gradual, and their cloud systems may extend far to the rear of the surface front itself. So you might get precipitation clouds behind a slow-moving cold front. Temperature and humidity are both going to drop or decrease. The pressure will rise, and the winds are going to shift from the southwest to the northwest upon frontal passage when we're talking about cold fronts. Now, a slow-moving cold front. The slope is on average 1 to 100. So 1 mile in the vertical to 100 miles in the horizontal. It's a very general upward motion of warm air along the entire cold frontal surface. You get pronounced lifting along the lower portion of the front. The pressure tendency, that change in barometric pressure, initially is either unsteady or a steady fall prior to the frontal passage, and then you get this weak pressure rise behind the front. Temperature and dew point, they're going to drop off sharply with the passage of a slow-moving cold front. The wind will veer with the frontal passage, so just like with the hands of the clock, it's going to move the wind's going to change direction in a clockwise manner, such as southwest ahead of the front, west to northwest behind the front. And it's going to the wind's going to reach its highest speed at the time of frontal passage with slow-moving cold fronts. The isobars, or those lines of equibarometric pressure, are curved in an anticyclonic fashion in the cold air, and this slow-moving front moves at an average speed between 10 and 15 knots. Overall, with a slow-moving cold front, the weather you get is going to depend on the stability of the warm air mass. When that warm air mass is stable, you get a rather broad zone of these mid-level altostratus clouds and nimbostratus clouds, and they generally extend several hundred miles behind the front. If the warm air is unstable, on the other hand, you get thunderstorms, you get these towering cumulonimbus clouds, these really tall growing clouds. They may develop within the cloud bank and may stretch for some 50 miles behind the surface front. In general, though, the ceiling or where the cloud height is, the cloud layer is generally going to be low with frontal passage, with gradual lifting after the slow-moving cold front moves through. Visibility initially will be poor if any precipitation, and they may continue to be reduced for many hours after frontal passage. Now, when the cold air behind the front is moist and stable, you'll get more of a low-level cloud deck of stratus clouds. You may even get fog, which may persist for a number of hours after the frontal passage. So here's a great schematic of a slow-moving cold front. In this case, the graphic on the left, I'm showing a colder air moving in, lifting the warmer air ahead of the front off the ground. That upward indicated arrows there near the nimbostratus word show that warm air being lifted. Now in this case, we have more of an unstable warm air mass. In the low levels, it's more stable with nimbostratus, but then look above it. Above the nimbostratus, you have the possible cumulonimbus if we have an unstable air layer, more in the way of showery thunderstorm precipitation with a unstable warm air mass. If you look at the graphic on the right, just showing you the relation of the upper level winds to the surface front, they generally tend to parallel the front. With a slow-moving cold front, the upper level winds are going to parallel the surface front, and that's why it moves slowly, because there's really no perpendicular component of the upper level winds to the surface front. So it moves very slowly with the upper air trough position to the rear of the surface cold front in this case. With a fast-moving cold front, on the other hand, this has a very steep slope. You have warm air near the surface being forced vigorously upward, a very fast-paced acceleration of air ahead of fast-moving cold fronts with a steep slope. At the higher levels of the atmosphere, the warm air is descending downward along the frontal surface. And fast-moving cold fronts can have slopes as steep as 1 to 40 to 1 to 80 miles. And usually this type of front is going to move very rapidly at 25 to 30 knots on average. This thing is moving quick, and it features a narrow but often violent band of weather ahead of it. If the warm air mass ahead of this front is if it's unstable, you get this line of thunderstorms that frequently develops along the front, and sometimes you get a line of very strong to severe thunderstorms that's 50 to 200 miles ahead of the front and parallel to it. This is known as that squall line and may produce damaging straight line winds. You know, you might think that a tornado went through an area when it's just these downdraft winds, these downbursts of winds, so strong that it literally produces damage. Now, when the warm air mass ahead of a fast-moving cold front is stable, on the other hand, you'll get more of an overcast layer of these mid-level altostratus layer-like clouds, and you may get rain that extend over a larger area ahead of the front. And then lastly, if the warm air is very dry, the atmosphere is dry, you'll have little or no clouds occur. And this can happen where you get cold fronts that move through and there's really no type of weather associated with it. You might just get a wind shift, for example, if the air is dry. So a fast-moving cold front is considered an inactive front. I want to point that out because lifting is going to occur only at and ahead of the front. The lifting is caused by descending air ahead of the front and only in part by the frontal surface itself. So fast-moving cold fronts, think inactive fronts, because the lifting is occurring at and ahead of the front, not at the front itself. And then with fast-moving cold fronts, you're going to get your pressure falls ahead of the front with a sudden and strong rise of the barometric pressure after frontal passage. If you get a squall line that is some distance ahead of this type of front, there actually may be a strong pressure rise associated with the squall line's passage, and you actually make it a temporary shift in wind. This can fool me. It can fool anybody. It's fooled me before. When you have a fast-moving cold front and you have the squall line, well in advance of the surface front itself, That squall line almost acts as if acts like a miniature front, and so you may get a wind shift behind the squall line. You may get a pressure rise behind the squall line, but then after the squall line's passed, the winds are going to return back to southerly direction, and the barometric pressure is going to level off. So then you'll really know when those winds go back southerly and the pressure levels off. Then you know that the actual surface front hasn't moved through yet. Temperature falls in the warm air ahead of the front are going to be caused by this evaporation of falling precipitation, this cooling effect. You'll get rapid clearing and adiabatic warming just behind the front, which tends to keep the cold air temperatures near that of the warm air. And then an abrupt temperature change usually occurs far behind the front, near the center of the high pressure associated with the cold air mass. So usually behind the cold frontal passage, you get an area of high pressure, which will then result in some nice weather after the front moves through. And the wind will veer or change direction in a clockwise manner with the frontal passage and is strong, gusty, and very turbulent mixing of air. Additionally, with a fast-moving cold front, you get cumulonimbus clouds, which are observed along and just ahead of the surface front. So these towering thunderstorm clouds form. You may get stratus, nimbostratus, and altostratus, the more layer-like clouds. They may extend ahead of the front in advance of these towering cumulus and cumulonimbus clouds. It may extend as much as 150 miles out ahead of the front. Showers and thunderstorms occur along and ahead of the front again with the fast-moving cold front, and visibility will drastically improve after the frontal passage. So here's an example of a fast-moving cold front. You notice how much taller these clouds are. You get some towering cumulus and cumulonimbus, a lot more atmospheric instability. The slope of this fast-moving cold front is much steeper, so you got a much more vigorous or accelerated lifting of the warm air ahead of the colder air. And the graphic on the right shows generally now that we have upper level flow, which is more perpendicular to this front. So you notice how the winds are from the northwest, and that more perpendicular upper level wind component is going to push the cold front much quicker, much faster through an area, and that's the push that these need to be considered fast moving. Now, there's some cases sometimes where you get secondary cold fronts to develop behind the main surface fronts, occasionally develop to the rear of a cold front in what's known as that trough, the area of lower pressure or heights. And secondary cold fronts usually occur during outbreaks of very cold air in the wintertime. And they usually develop behind the initial outbreak itself. And secondary cold fronts may follow in intervals of several hundred miles to the rear of a rapidly moving front. And when that secondary cold front forms, the primary front usually washes out or dissipates. And then the secondary cold front becomes the primary front from that point forward. Secondary cold fronts, again, primarily a winter feature, do not occur during the summer months. Right, and then we'll talk about a few more things today in the training. We're going to run into a topic here on cold fronts aloft. We'll talk about that. We'll talk about warm fronts, occluded fronts, and stationary fronts. So we'll run into that, and then we'll probably going to divide this up into two parts. I'll do two parts of the video since it's such a lengthy topic. I'm going to run through the frontal systems and then we'll cover the rest of the topic next week. All right, so for cold fronts aloft, there's generally two types. One is the upper cold front associated with a warm occlusion, and the other occurs frequently in areas east of the Rocky Mountains in winter. It's associated with maritime polar air crossing the mountains behind a cold front or behind a cold front or a cold trough aloft and a very cold layer of continental polar air lying next to the ground east of those mountains, such as the Rocky Mountains. So you get this warm, moist tropical air that's moving from the Gulf of Mexico northward. That air is going to be forced aloft because of how light it is. It's very light, the warm, moist air of the Gulf of Mexico, the maritime tropical air mass. And you have colder continental polar air at the surface. Then you get this cool maritime polar air that flows over the mountains aloft. and it forces its way underneath the warm, empty air aloft. And this is going to result, the resulting front occurs and flows across the upper surface of the colder continental polar air as if it were the surface of the ground. Here's an example of it graphically, and this will probably make more sense. But in the wintertime, you may have cool maritime polar air moving in aloft over the Rocky Mountains. At the surface, to the east of the Rocky Mountains, we have this very cold continental polar air mass, which is very cold and dense. And you see this warm maritime tropical air mass, which is the lightest of all the air masses. That tends to rise in the vertical because of its buoyancy or less density. So the result is going to be an upper front, cold front. The colder air on the west side, or the windward side of the Rocky Mountains, is not going to be able to go through the mountains, so that air is forced up and over the mountains as cool maritime Pacific air. And there you have it. All right, so weather from cold fronts aloft, these can be very significant. This can produce that extensive cloud deck and blizzard-like conditions for several hundred miles over the Midwestern plains, east of the Rocky Mountains in the winter season. When you got three different air masses here colliding, we already have the warm tropical air mass being lifted in the vertical, riding up and over the colder continental polar air at the surface. And then when you throw this cool maritime Pacific air underneath the warm maritime tropical air, you can get some explosive cyclone development and get these blizzards to occur. And that's the significance about cold fronts as they move aloft over the mountains. Now let's move into a discussion on warm front. A warm front is a line of discontinuity where the forward edge of an advancing mass of relatively warm air is replacing a retreating colder air mass. So we got warmer air moving into an area, and it's initially when the warm air moves into the area, it's going to be much less dense, and it's going to ride up and over colder air at the surface. The slope of this type of front, the warm front, is on the order of 1 to 100 to 1 to 300. So 1 mile in the vertical to 100 to 300 miles in the horizontal, with occasional fronts with lesser slopes, even lesser than that, more gradual than that. Characteristically, you have shallow slopes associated with warm fronts. This is caused by the effect of surface friction that's going to slow the motion of the front as it's near the ground. It's going to slow that frontal movement. Warm fronts move slower than cold fronts with an average speed between 10 and 20 knots. With the pressure tendency with the barometer, if you're going to ahead of the front, is usually you're going to have a rapid or unsteady fall of pressure with a leveling off of the pressure after frontal passage. The wind will increase in advance of the warm front because of a steeper pressure gradient and will then reach a maximum just prior to frontal passage. Additionally, with warm fronts, the wind is going to veer with frontal passage. Usually, it's going to change direction at the surface from the southeast to the southwest. So southeast ahead of the warm front, southwest behind the warm frontal passage. Temperature is going to be fairly constant or even slowly rise in advance of the front until the surface front passes. And then, of course, after the warm front passes, those temperatures will really show a marked increase or rise. The dew point, or measure of the humidity, this usually is going to increase slowly with the approach of the front, followed by a rapid increase in precipitation in fog areas. And when you have dew points in areas of precipitation and fog areas, we have saturation reached in a lot of cases. So with warm fronts, another really cool real cool thing about these type of fronts is they show a noticeable cloud sequence in the following order. Initially, you're going to see those high, wispy cirrus clouds well in advance of a warm front. Eventually, those cirrus clouds are going to lower to cirrostratus, to then mid-level altostratus, and then lowering to nimbostratus and stratus as the warm front gets closer. So this is a constant indicator by looking up into the sky and noticing the changes in the cloud types as far as a warm frontal passage. Cirrus clouds may appear, in fact, 700 to 1,000 miles or more ahead of the surface front, followed by the cirrostratus clouds about 600 miles ahead of the front, and then altostratus clouds about 500 miles ahead of the surface swarm front. Precipitation in the form of continuous or this intermittent rain, snow, or drizzle is frequent, as far out as 300 miles ahead of the surface swarm front. Surface precipitation is associated with these nimbostratus clouds in the warm air above the frontal surface and with stratus clouds back in the colder air. Now, when the warm air is convectively unstable, you can get these showers and thunderstorms that develop. By the way, fog is common in the colder air ahead of the warm front. So here's a great look at warm frontal types, generally showing you the difference between stable warm air on the left and unstable warm air on the right. And you'll notice the abbreviation of the letters represent the different cloud types. Again, the general sequence of the warm front for the cloud types, initially you'll see the wispy, feathery cirrus clouds, and then those are going to lower to cirrostratus, altostratus, nimbostratus, and eventually stratus. You may, with a stable warm air mass, you're looking at more of a stratiform, very layered cloud structure. You may get continuous rain or snow, and you also would get more in the way of fog. Now, if the warm air mass is unstable on the right, you have a steeper slope associated with it, right? You're going to get more showery precipitation. You're going to get a buildup of the clouds. They're going to become more puffy looking, more unstable looking, towering cumulus and cumulonimbus, very possible when the warm air mass is unstable. So a big difference. With warm fronts, clearing usually does occur after the passage, after frontal passage, but at times you could still see drizzle and fog, which may occur within the warm sector. Warm fronts are generally going to move in the direction of the isobars, or lines of equal barometric pressure, of that warm sector, usually to the east and northeast of the northern hemisphere. That's the general direction of warm fronts. And the amount and type of clouds and precipitation is going to vary depending on whether the front is active or inactive. With active fronts, there's a strong overrunning and pronounced prefrontal clouds of precipitation, whereas with inactive fronts, you get more of a broken cirrus and altocumulus clouds are common. Next, we move on to a discussion on occluded fronts, and then we will end today's training with a discussion on the stationary front. So, an occluded front is a compromise of two fronts. They form when a cold front catches up and overtakes a warm front, and one of these two fronts is lifted aloft. The warm air between the cold and warm front is going to be shut off as the cold front catches the warm front. Maybe either a cold type or a warm type. There's two types of occlusions, warm and cold type. The type of occlusion is going to be determined by the temperature difference between the cold air in advance of the warm front and the cold air behind the cold front. So let's first talk about the cold type of occlusion. And this is going to occur when the colder air in advance of the warm front is warmer than the colder air to the rear of the cold front. So what we're saying with a cold occlusion is the coldest air is going to be behind the cold front. Overtaking a cold air undercuts the cool air in advance of the warm front. So this is going to result in a section of the warm air being forced aloft. The upper warm front will follow the surface occluded front by 20 to 50 miles, and cold type occlusions are more frequent than warm type. With the warm occlusion, this occurs when the air in advance of the warm front is colder than the air to the rear of the cold front. So in this case, with warm occlusion, we have cold air behind the cold front, but the coldest air is ahead of the cold front. So when the cold air of the cold front overtakes the warm front, it's going to move up and over this colder air in the form of upper cold front. And the upper cold front is going to precede surface occluded front by as much as 200 miles. Some of the characteristics of an occluded front. Now, what makes these unique is they have the characteristics of both the cold and the warm front type of weather. So you could have the cold front's narrow band of violent thunderstorms, that violent weather, and the warm front's widespread areas of cloudiness and precipitation. The occluded front, most violent weather is going to occur at the apex or the tip of the occlusion. The The apex is the point on the wave where the cold front and warm front meet to start the occlusion process. So your most violent conditions or weather occurring at that apex or the tip of the occlusion. That's very important. Here's an example of an occluded front showing you the different types of clouds and precipitation you'd have with the cold occlusion. Notice that the coldest air is going to be behind the cold front. In this case, we got a warm front aloft as the warm air has been lifted off the ground. And we get a lot in the way of, with cold occlusion, you get more typical, you see cold front type weather, where you get more in the way of showers. If the warmer air aloft is unstable, there's a great possibility you could see some towering cumulus clouds and perhaps some cumulonimbus with the cold occlusion. Meanwhile, the warm occluded front, the coldest air is going to be out ahead of the surface cold front. Warm air is again lifted aloft, and with the warm occlusion, you typically see more in the way of warm frontal type weather with more continuous showery precipitation and more of a stratus deck in the low levels. And yeah, aloft, as that warm air is lifted aloft, you definitely can see some more in the way of towering cumulus. But in general, the weather at the surface of warm occlusion tends to follow more that of a warm frontal weather. Stratiform clouds, more continuous precipitation. And today's training, we'll talk about the last type of front, which is known as a quasi-stationary front. This is a front along which one air mass is not appreciably replacing another air mass. It may develop from the slowing down or stopping of a warmer cold front. The slope of the warmer cold front is initially very shallow, and you get this dense cold air which stays close to the ground, and the warm air is displaced slowly upward along the stationary frontal boundary. The front slows or stops moving because the winds ahead and behind of the front become parallel to the stationary front. So again, why is this front not really moving very quickly? It's moving at less than 5 knots of speed, by the way. And it's because the mid and upper level winds are blowing parallel to the surface front, so there's really no push of the surface front. The front is made up of small waves which undulate back and forth along the front. And there's 2 types of stationary fronts. There's the stable and unstable. So with the stable stationary front, you get this warm air which rises up and over the surface front, and it causes a slow upglide of air. As the air is lifted slowly and gradually to saturation, you get clouds that form in the warm air above the front. Stable type of stationary front has a shallow slope, more layer-like clouds and drizzle, and if you're flying through this area, there's icing considerations, definitely, which may develop above the freezing level at temperatures below that 0 degrees Celsius point. Now, if the slope is steeper and significant warm air is being infected or moved up at the frontal surface with a stable front, stratus clouds with embedded showers occur. Now, with an unstable stationary front, you get a steeper, the slope is shallow, but it's a little bit steeper, a little bit more steeper than the stable stationary front. Sufficient lifting occurs, clouds that are more of the cumulus type, or sometimes you get a stratiform level or layer of clouds, and you get these towering cumulus clouds embedded within the stratus deck. If the energy release is great, where you have this warm, moist, and stable air mass in place that's lifted, you get thunderstorms that develop. All right, and again, icing is a consideration for this. Really, it comes down to the slope of the unstable stationary front. Is it shallow or is it steep? That's really going to determine your weather. And there is your graphics showing a shallow stationary front at A, with much more gentle upglide, much more shallower frontal slope, with a shallow stationary front, more stable. The steeper slope is associated with more unstable stationary front. All right, I am going to end this presentation at the fronts and mountains. Mountains definitely do impact fronts, for sure. I certainly hope you enjoyed this training today, but I'll go ahead and end it here since we've been going pretty long. Looking forward to future topics here in the future here at Spot on Weather. Thank you again for subscribing to our channel. We certainly have a passion for the weather. and we love sharing that passion with you. All right, that wraps things up on today's training on fronts. Hope you learned something really well. Thank you again for becoming part of our Spot on Weather family. Take care, everybody, and have a great day.